So you say that also. So that must also annihilate, but that means that this is 0. So this is 0. So that's why this is equal to 0. But what does that mean? But this holds for all I, right? This holds for all I equals to 1, 2, all the way out to n minus k. Therefore, the Lie bracket is in the mutual kernel. It's in the common kernel of all the local defining one forms. But that is precisely the definition of the distribution as is given by differential forms. So this being 0 for all k immediately implies that the bracket is an element, is itself a local section of D. And that there's the equivalence is proved, okay? I don't know. I start to get happier the more I do with differential forms, and like when I can switch from vector fields to the differential forms and start to understand things, it's very exciting for me, because I always get to this point in the course and then the semester's over. So this is where I want to live. I want to just spend all of my life here understanding these things more. But inevitably the course ends, and then I'm back to square one until I teach it again. I guess I could just read. I could just read and learn for myself, right? I mean, you don't have to teach to learn, right?
I guess.
You know?
I guess you have to do it if you're being taught, if you're teaching that.
Well, if you don't learn before you teach, it does make it tricky to teach. That's true. So this proposition 19.8 is nice. It has, so you have D a distribution, rank K, and you've got omega 1, omega 2, omega n minus k, smooth defining one forms for D, all right? Then the following are equivalent. A, D is involutive on U. B, the d omega 1 throughout d omega n minus k annihilate D. A-N-N-I-H.
Is it?
Yeah, well, it says here. And then C, there may be a British spelling. Maybe you're British. Let's see here. There exist smooth forms, one forms, alpha, upper I, lower j, for I comma j equals 1, 2, all the way out to n minus k, such that d omega I is equal to the sum j equals 1 to n minus k of omega j wedge with alpha ij. And he goes on to describe what this means in terms of abstract algebra, all right? He says, an elegant way to express the involutivity condition in terms of differential forms is to notice that what we really have here is an ideal in the exterior algebra. An ideal is a subspace. So like an ideal would be like J as subset. So he puts the star up here for like all possible forms. So this is the total exterior algebra. So J is an ideal if you have like eta wedge omega is an element of J for all eta in omega star M. Right, so in here I wanted omega to be an element of this. Okay, omega is an element of J for this discussion. So that's what's called an ideal in this context. And another way to look at this proposition is that this ideal is actually it's closed under the differential as well. Like, dj, if you will, is a subset of J as well. This is called a Pfaffian system, and it's said to be a differential ideal if it meets that condition. Anyway, okay, so let's get to the end of this here. So what's the Frobenius theorem? We're kind of dancing all around it, but the Frobenius theorem has one other further idea, which is completely integrable. And so completely integrable is actually what we've already seen in like example B from the start. That kind of chart is a flat chart. But let me not. I think we're out of time. I don't think I have time to write up everything here. Let me just write. I'm going to write it in words. I'm going to cheat you guys out of a definition here. So, excuse me. So he points out that I don't want to erase anything. I love it all too much. All right, you go on. That's it. Haha. We don't need you anymore. You had a question about that one? Yeah, nicely done. So, Frobenius theorem. So here's the theorem of Frobenius. It says that every involutive distribution is completely integrable. And this completely integrable means that you can find a chart which makes the manifold look like example B, essentially. It basically forces the manifold to line up with the distribution that you have in a very nice way, so that you can chop the manifold up into pieces that align with this distribution, and also the pieces which are perpendicular to the distribution in some sense. And so this just gives us an incredible tool to like take manifolds apart into pieces, basically. And he has this powerful example, 1914, where he actually has a non-trivial distribution of 3 dimensions, and he walks you through a calculation which shows you how to build that chart in that context. And that's one of your homeworks, is to work through that, so yay. And let's see here, anything else I want to tell you? So I hope I've showed you enough that you can, like read this chapter and get more out of it. I've given you some examples of foliations, but he has careful technical definition of foliation, like later in the chapter, pages 501 to 502, he describes carefully what is a foliation. And he has some pictures of like different ways to foliate a torus. For example, you can, anytime you have 2 manifolds like M cross N, there's a natural foliation of 2 manifolds by just fixing a point in one and just letting the other one be the full thing, or vice versa. So if you've got like M cross N, the product manifold, there's natural foliations into like points across the other manifolds. But there are other things, like this irrational wind on the torus gives a different foliation. Every point is hit by a unique, it's hit by that foliation just once, but that's weird. Then he's got this global Frobenius theorem, let D be involutive distribution on a smooth manifold. The collection of all maximal connected integral manifolds forms a foliation of M. So it kind of puts everything together in terms of the taking a manifold and chopping it up into pieces with respect to a given distribution, if that distribution's maximal. Here's some rather adventurous pictures of such a process, right? Chopping it up into pieces like that. Then he applies some of these things to Lie algebras and Lie subgroups. And so his theorem 19.6, he says, suppose G is a Lie group and frac G it's Lie algebra. If frac H is any Lie subalgebra of G, then there exists a unique connected Lie subgroup of G whose Lie algebra is H. That's pretty amazing. It says for any Lie subalgebra, there exists a Lie subgroup, which takes it as its tangent. And so that's proved with the technology of this chapter. It's pretty cool. And then finally, he applies these ideas to overdetermined systems of partial differential equations, which is, I think, something very interesting and really deserving of its own course. There's something called exterior differential systems. I can't spell. Exterior differential systems. EDS. And like if you read the book Cartan for Beginners, it gives you this look inside this whole vast world of further things you can do with differential forms and these things. It goes far deeper than we're seeing right here. And I think all of these things were known to basically what that book more or less says is like Cartan knew many things and we're still just starting to understand them. Kind of to summarize, it's kind of funny when a person does such great work that some of his elementary results are really the more appreciated ones, and the deeper things just are kind of hidden in plain sight for future researchers decades and decades and generations after to find. Who knows if there's not stuff like that in Newton's work. So that's chapter 19. Now, I'm not like fully covering past this point. So I have some like token homework problems. You should be able to answer those by just like reading. I have a few more things to say about chapters, like 20 and 21. 20 not so much. 20 really just have like a token comment. So my token comment for chapter 20. So chapter 20 is on Lie groups, and so can I erase all this? Actually, I'm going to go to the middle board. I'm going to the middle board here. Oh, come on. Are you guys okay for 20 minutes? Or is that too long? I don't know where are we at? You should go soon? Okay, so I'll say, oh, yeah, probably. All right, well, I will try to limit myself to 5 minutes. Is that okay? Is that okay? Okay, I'll try to say what I got to say in 5 minutes. So in a nutshell, the next chapter on Lie algebras and Lie groups, it's very nice. He uses the Frobenius theorem to prove various things. He develops the exponential on a Lie group as it relates to the Lie algebra. So like the like here's what it is. If you have x is in the left invariant vector fields on the group, then and say gamma is integral curve with gamma of 0 equal to 1 element, then the exponential of x is by definition gamma of 1. All right, there you go. That defines the exponential on a Lie group, just like that. And he proves that for a matrix Lie group, this is the matrix exponential. So like special case, G, a subgroup of GLN R, you can, under the usual identifications, the exponential of TA is, for lack of imagination, gamma of 1. It is the matrix exponential is this abstract exponential. All right? Now, and he proves that. He also proves that there's a correspondence between Lie groups and Lie algebras. He says in theorem 20.19, if G and H are Lie groups, G is simply connected, and if frac G and frac H are their Lie algebras, then if you have any Lie algebra homomorphism, frac G to frac H, then there exists a unique Lie group homomorphism, big phi, from G to H, such that, get this, the differential of phi is exactly little phi. So there's this wonderful interplay between Lie algebras and Lie groups. You can understand one from understanding the other. This is the Lie correspondence. Theorem 20.21, there's a one-to-one correspondence between isomorphism classes of finite dimensional Lie algebras and isomorphism classes of simply connected Lie groups, given by associating each simply connected Lie group with its Lie algebra. So in order to understand the possible structures of Lie groups, you can simply classify what the possible Lie algebras are out there. There's something called representation theory, which gives concrete answers to the possible patterns that Lie algebras can fill out. There's a well-developed theory. There's like 5 infinite families, and there are these other exceptional Lie algebras. There's like tons known about this, all right? And the start of that is given in his adjoint representation. He talks about it at the end of the chapter. Things, and then chapter 21, yeah. How many minutes do I have?
It's 5:05.
So do I have like 5 minutes still, or? Okay. So chapter 21, chapter 21 is on quotient manifolds, and just want to hit the highest of high points in here. What's that?
This is the chapter we studied from this.
Yes, this is true. And what? Yeah. Fine. I will eat 20 minutes of next class on this one. I can't do this in 5 minutes. But what I can do in 5 minutes is finish what I have to say about Lie groups. Something that's not in Lie, but I think I want to tell you guys about, is the matrix exponential. Here, check this out, guys. If I have e to the a times e to the b, do you know what happens?
A plus b.
A plus b, right? Except that that's wrong. It's not wrong, it's just incomplete. What's the next thing?
Plus E, B plus A.
Plus 1/2 the commutator of A and B. We're not done. What comes next?
It wouldn't be
Plus
incorrect.
1.
How do you make jokes?
Plus 1/2 commutator of BA.
Well, that would be 0. But what I was looking for was 1/12 the commutator of A with the commutator of A with B, plus 1/12 the commutator of B with the commutator of B with A. And this isn't entirely truthful. Like, I just don't remember. So this is actually plus or minus. This is actually plus or minus. I don't remember. One of them's plus, one of them's minus. I don't remember. Okay? Oh, and that's not it.
Oh, yeah, I guess.
And then what's next is thrice-nested. Thrice-nested commutators. Commutators of commutators of commutators of commutators of commutators of commutators, and so forth. What's that?
Is it 1/144?
I have no idea what the next term is, actually. But this is the BCH, or BCH relation, the Baker-Campbell-Hausdorff relation. So check it out. What does it say? These right here are in the matrix group, right? And so what we have is exponential is a mapping from the Lie algebra to the Lie group. And notice that in a neighborhood of the identity, the structure of the Lie algebra completely fixes the multiplication of the group. What am I saying? Think about this. Because you have this formula, if you know what the Lie brackets work out to, that tells you how to multiply. Like, if the Lie algebra is abelian, if all of the brackets are 0, e to the a times e to the b is simply e to the a plus b. But if all the brackets are not 0, then this tells you when you multiply e to the a times e to the b what happens when it's not commutative. The Lie algebra tells you how to multiply. This is called exponentiation in physics. We exponentiate the Lie algebra to get the Lie group. So this viewpoint is not really found in Lie's book as far as I can cipher. But this is how I was taught. Anyway, that's it for today. Next time we got like 20 more minutes in Lie, and then I am making a hard segue to like calculus 3 you guys didn't learn. So it should be refreshing, I think.